Okay, so the first speaker is Ryui Kaneko from Kina University. So he will tell us about the Tensor-network study of correlation spreading dynamics in two-dimensional systems. Okay, so Kaneko-san, please go ahead.
Yeah, thanks for the introduction. So today I'm going to be talking about the tensor network study of the quench dynamics in the Bose-Hubbard model and also in the quantum Ising model and using infinite PEPs. And this work has been done with Dashida-san. And part of our results are given in this recent archive paper. So this is the outline of my talk. I divide my talk into two parts. In the first part, I will focus on the quench dynamics of the Bose-Hubbard model. And yeah, motivated by the recent analog quantum simulation, we study the quench dynamics of the Bose-Hubbard model using the 2D tensor network method based on infinite PEPs. And I found that numerical simulations obtained by PEPs recover the experimental results very well. And after that, I considered the parameter regions, which hasn't been explored by the experiment, and considered the quench dynamics and did the simulation. And I also estimated the group and phase velocities in that parameter regions, which may be helpful for future experiments. And if time allows, I will also focus on the quench dynamics of the transverse field Ising model, which is also motivated by the recent analog quantum simulation using Rydberg atom arrays. So I will first move on to the first part. Recently, analog quantum simulation has attracted much interest, and using a quantum gas in optical lattice, one can do a simulation of real-time dynamics. And in the experiment, starting from the mode insulating state, one can consider sudden change of the parameters in the Hamiltonian, and one can consider quench dynamics near the parameter region here. And during this kind of real-time dynamics, it is also interesting to study how quantum information propagates. For example, I showed an example in one-dimensional case here. When we consider a quench dynamics, starting from the mode insulator, quasi-particles emerge. This blue guy corresponds to the quasi-particle having an empty site, and this red guy corresponds to the quasi-particle having doubly occupied site. Then these two guys move to the opposite direction, and this propagation velocity can be obtained by dividing the distance between these two divided by time. So we can examine this kind of quench dynamics behavior in the experiment. For this purpose, experimentalists often measure the equal time correlation functions, which can be also calculated by using some kind of numerical simulation. So it is often important to compare the results of the numerical results and also experimental results to examine how accurate the experimental results. And indeed, in one-dimensional case, using the ytterbium Bose-Hubbard simulator, single particle correlations are studied. These red points correspond to the peak time in the correlation function, and they plot this peak time as a function of the distance, and it shows almost linear behavior. So from this slope, they estimated the propagation speed, especially the group velocity, and they concluded that this value doesn't exceed the expected upper bound, so-called Reed-Robinson value. And also, theorists considered numerical simulations using 1D case using MPS, and they also obtained similar results. So in this case, experiment and numerical results agree very well. And not only the correlation functions, conservation of the energy is another subject to be compared. Here we showed each energy, and this green line corresponds to the sum of the kinetic energy and on-site interaction energy. And when we considered a quench dynamics, this sum of the energy should be conserved for relatively long time. And this shows the experimental results and MPS numerical simulations in 1D, and this corresponds to the three-dimensional case using some kind of semi-classical approximation, so-called truncated Wigner approximation. And in each cases, experimental results and numerical results agree very well. However, it is really difficult to simulate this kind of numerical simulations in 2 dimensions. So numerical simulations in 2-dimensional systems are not so many. So we are interested in simulating this kind of quench dynamics in 2 dimensions. So we use the 2D tensor network method, basically based on the projected entangled pair state. And what we did is, as in the experiment, we focus on, we consider starting from the mod insulating state and control the parameters of the Hamiltonian suddenly. So we consider quench dynamics as in the experiment. And in the first part, I will focus on the quench to the mod insulating region as in the experiment and compare the numerical results with the experiment. And after confirming the accuracy of our results, we focus on the rather smaller, rather weaker interaction regions to obtain propagation velocities. So in our simulation, we used infinite projected entangled pair states, infinite PEPs, or so-called infinite tensor product states. In the Bose-Hubbard system, the dimension of the local Hilbert space is not bounded. So we have to carefully choose this dimension of the local Hilbert space, bond dimension, physical bond dimension. In the presence of interactions, however, this dimension of the local Hilbert space is effectively bounded. So we don't have to choose infinite bond dimension. And so in practical calculation, we chose sufficiently large bond dimensions so that all the correlation functions are well converged. We are interested in how far one can go by just using the PEPs. So we are interested in the applicability of the PEPs. So we take the simple PEPs, infinite PEPs for having 2 site unit cells, and also apply the rather primitive real-time evolution technique, which is a TEBD-like simple update algorithm, rather than taking the sophisticated full update algorithm or variational update algorithm. Here I show the previous studies of the tensor network method, tensor network results in the transverse field Ising model case. I think, if I remember correctly, I think they use some kind of full update-like algorithm, and they consider the certain quench starting from the disordered state and quench the parameter to the exactly at the transition point. And they calculated the transverse magnetization and also energy error as a function of time. And these results are obtained by Kozalnik and his co-authors. And according to their study, they found that when the bond dimension becomes larger, all the physical quantities seem to be well converged. And up to a short time, approximately up to inverse of the interaction, they obtained rather accurate physical quantities. So we apply this kind of method for the Bose-Hubbard system. So our numerical setup is given here. We consider the square Bose-Hubbard model in 2 dimensions. As for the static property, there are many studies on the Bose-Hubbard model. And also, Jerome gave the presentation yesterday that even a 3-dimensional Bose-Hubbard model can be studied using Pep's type algorithm. But here, we will focus on the quench dynamics, real-time dynamics of the 2-dimensional Bose-Hubbard model. And here we consider very fast parameter change or sudden change of the parameter, sudden quench of the Hubbard systems, starting from the Mott insulating state. In the experiment, actually they consider parameter change, on-site interaction U, starting from 100 to nearly 20. This value 20 corresponds to the value here near here. It's actually in the Mott insulating region. So for the finite time quench, we consider this kind of parameterization. For the calculation of the quench dynamics, we use the Tensor-network library TNS, which is developed recently in ISSB. So here we show the part of the results. Let's focus on the energy conservation first. We plot the energy as a function of time for bond dimensions 6, 7, 8, and 9. As you can see, they seem to be well converged. And for the short time, the energy is nearly conserved. It seems that the energy is conserved for up to time around 0.4. And let's focus on the physical quantities for this short time. So these values are obtained up to time around 0.5. And we plot the single particle correlation functions for obtained by Pep's simulations. And for comparison, we also did the exact diagonalization for the rather small system sizes, 9, 12, 16, and 20. So the largest exact diagonalization results are given for the darker gray lines. And as you can see, up to, well, the exact diagonalization shows rather large size dependence. On the other hand, Pep simulations give rather small bond dimension dependence. So I think that the result of the Peps is almost converged. And by comparing these two results, as you can see, for the distance 1, the single particle correlations are almost the same up to short time. So we think our results are not so bad. And also, even the case of distance 2, even though the exact diagonalization shows a large size dependence, the Pep's results are almost converged. And it seems that when we extrapolate the exact diagonalization results, this kind of peak structure, it seems to converge to the Pep's result. So I think Pep's result is much more reliable. And this result was obtained for the sudden quench. Here I consider a finite time quench as in the experimental result. Even in the case of the finite time quench, we observed that the energy is nearly conserved for a short time up to around 0.4. And we also compare this being a single particle correlation obtained by the experiment given in the red point. As you can see, Pep's results and experimental results overlap very well. For the short time, around 0.4, where the energy is nearly conserved. We also compare the peak position, peak time for each distances and plot these results here. And experimental results and also numerical results agree very well. And having confirmed the applicability of our PEPS algorithm for rather stronger interaction region, we try to study what happens when we consider weaker interactions, which hasn't been explored by the experiment. So actually, during the real-time evolution, we have two types of characteristic velocities. One is the phase velocity, and the other is the group velocity. And the phase velocity is characterized by the velocity of the wave packet given by this blue oscillation. This first peak characterized the phase velocity. And this is determined by the energy scale of on-site interaction U. On the other hand, we also have the group velocity, which is characterized by the envelope of the wave packet. And this guy is determined by the energy scale of the hopping J. So when U is much larger than J, these two velocities split. And this kind of behavior are actually obtained by using strong coupling approach, previous studies. But if you consider the case where U and J are comparable, we may expect that the phase and group velocities are nearly the same. So we want to obtain this kind of how they behave for smaller, weaker U interaction. But unfortunately, we cannot do such a long time simulations. We have to somehow estimate the phase and group velocity for the short time numerical results. And empirically, it is actually possible. And empirically, this kind of phase velocity may be obtained by using single particle correlation function. On the other hand, the group velocity may be obtained by using the density correlation functions. So with this, we use this kind of two correlations to estimate the velocities. So here is the result of the each correlation function for weaker interaction. And here we show the energy as a function of time for each interaction. In the case of stronger interactions, we previously observed that the energy is nearly conserved for a short time up to 0.4. But when we consider weaker interaction, the energy is nearly conserved for around 0.9. So the energy conservation time is relatively longer for smaller U. And for this parameter region, we show a single particle correlation here and density correlation function here. And by picking up this first peak time for each distances, we plot these data here for the for single particle correlations and density correlation function. In the case of single particle correlation, this slope is rather large, which means that the velocity may be relatively large, relatively faster. On the other hand, for the density correlation, this slope is rather small. So the velocity is relatively slower than the velocity obtained by the single particle correlations. So as expected, the phase velocity obtained by the single particle correlation is slightly faster than the group velocity obtained by the density correlation function. And I summarize these results obtained for each interaction U here. The blue points correspond to the phase velocities estimated from the single particle correlation functions. And the red points correspond to the group velocity estimated from the density correlation function. And for smaller interaction, it is expected that the single particle picture holds. So we can expect that the group velocity should be around 4. And our result also is consistent with this kind of behavior. On the other hand, when the interaction is much larger in the large interaction regions, we can expect quasi-particle picture. So in this case, these guys obtain this kind of some kind of form for the group velocity. And we found that we didn't consider a very strong interaction region, but at least for the interaction near 20, we obtain this kind of group velocity similar to the expected result. And then we, in the analytical, there is no upper bound for the group velocity obtained in the intermediate region, but we numerically found this kind of behavior in the intermediate region. So these kind of velocities may be used for future experiments. So I summarize the first part of my talk. So I did the simulation. Using the 2D tensor network method based on infinite PEBs, we simulate the quench dynamics of the Bose-Hubbard model. And in the first part, we consider the parameterization similar to the experiment and obtain the numerical results, which is consistent with the experiment. After that, we consider a weaker interaction region and estimated the phase and group velocities, which may be tested in the future experiments. I think I still have some time, so let's move on to the next topic, transverse field Ising model. So in the previous plot, I focused on the quench dynamics of the Bose-Hubbard model. Here we focus on the analog quantum simulation of the quantum Ising model, which can be done using Rydberg atom arrays. In this experimental setup, the Ising interaction can be obtained by van der Waals interaction of the Rydberg atoms. On the other hand, the Rabi frequency or detuning of the lasers can be mapped to the transverse field or longitudinal field in the effective quantum Ising model. So by controlling these parameters in the experiment, we can generate this kind of effective quantum Ising model and study many body systems. And actually, recently, these qubits the number of qubits exceeds 200. So even a two-dimensional system can be experimented. So here I show the previous papers on the quench dynamics or sweep dynamics of the quantum Ising model. And they compare the results with the MPS simulations for two-dimensional systems. But they actually show really good results. But it is also important to compare this kind of results using other numerical methods. Well, in today's talk, I will not focus on this experiment explicitly, but I will just focus on the simpler quantum Ising model. But our results may be useful in this kind of future experiments. So in the experiment, people can measure the equal time correlation functions. So it is also helpful to calculate equal time correlation functions numerically using infinite PEBs simulations. And there is another interesting topic here. In the previous Bose-Hubbard system, we estimated the phase and group velocities. Actually, the group velocities should have the upper bound, so-called Lieb-Robinson bound. And this Lieb-Robinson bound is often obtained, rigorous result of the Lieb-Robinson bound is often obtained in one-dimensional systems, but in two-dimensional system, it is not so rigorous. I mean, we can obtain rigorous upper bound, but the upper bound is sometimes so loose, it's not so tight. And actually, very recently, the Lieb-Robinson bound has been updated and it becomes much tighter. So we want to compare how tight, we want to investigate how tight the recently updated Lieb-Robinson bound by comparing the group velocity obtained by the IPIPS simulations. So this is our motivation. One is to study the correlation functions in the quantum dynamics of the two-dimensional quantum Ising model, and the other motivation is to study how tight the Lieb-Robinson bound is. So here we focus on the quantum Ising model in two-dimensional system and consider a quantum dynamics starting from the disordered state. So the initial state is the ground state of the infinite transverse field, omega equals infinity, and quench the systems to the parameter region close to the transition point. For simplicity, we focus on the nearest neighbor Ising interaction. In the realistic experiment, it should be van der Waals interaction, so it should be very long range. But since the decay speed is really fast, out to the power of 6, we just consider the nearest neighbor interactions here. And we consider the parameter regions, two parameter regions. One corresponds to the line without effective longitudinal field, and the other is the parameter where the longitudinal field is around 0.5. So let's focus on the benchmark results for the ferromagnetic Ising model in the presence of the transverse field. I compare the spin-spin correlation functions and transverse magnetization for our PEPS results and previous PEPS and artificial neural networks results. Here I consider the quench to the at the transition point. As you can see, our results agree very well with the previous artificial neural network results. And I also want to mention that in the previous artificial neural networks, the system size is for finite systems, so 8 by 8. So the longest distance would be distance 4. And I think their results for distance 4 may not be converged. On the other hand, our result is basically for infinite algorithms. So I think this longest distance correlation would be much more accurate than previous results. But in any case, qualitative behavior are almost the same between our results and previous studies. And after that, we also try to estimate the propagation velocity from the peak time of the correlation functions. We pick up the first time peak for each distances and plot the time as a function of the distance here. As you can see, the peak time is nearly proportional to the distance. And from this slope, we can estimate the propagation velocity. But we have to be careful because we don't know whether this velocity corresponds to the group velocity or phase velocity. So before investigating the velocities for several parameter regions, we first try to find whether we can find the region where group velocity and phase velocity become nearly the same by just using the exact diagonalization method. By using the exact diagonalization method, we cannot calculate the longer distance correlation functions, but we can at least try to find the parameter region where the wave pocket of the envelope of the wave pocket exists or not. For example, if we consider large transverse field, omega equals 5K, we clearly see the envelope of the wave pocket. So this behavior suggests that the group and phase velocities may be different in this parameter region. And this kind of envelope behavior still exists for rather smaller transverse field, omega is 4 and omega equals 3. But when we consider omega equals 2, it seems that the group and phase velocities are nearly the same. So we focus on the parameter region, omega, transverse field, omega is smaller than 2. And this is the result obtained by the IPIP simulations for the ferromagnetic Ising model with the transfer field case. So since for the parameter region, omega smaller than 1.5, our results didn't converge for the bond dimension up to d equals 9. On the other hand, for the bond dimension, for the parameter region, omega larger than 1.5, our results seem to be well converged. So let's focus on this parameter region. And also, when omega becomes much larger than 2, we may see the phase velocity rather than the group velocity. So since we are interested in the group velocity, let's focus on this reliable part given in pink region. And we also compare the recently updated Lieb-Robinson bound here. As you can see, the estimated Lieb-Robinson bound, recently updated Lieb-Robinson bound, it's much larger than our estimate of the propagation velocity, the group velocity. So I think there may be a room to improve the recently updated rigorous Lieb-Robinson bound. We also study these velocities for the antiferromagnetic Ising model in the presence of both longitudinal and transverse fields. Well, in this case, there is no study. There was no previous studies on the Lieb-Robinson bound, but we obtain similar propagation, the group velocity here. And this value may be used for the future experiments or future rigorous studies on the Lieb-Robinson bound. So I summarized my results on the quantum Ising model, the quench dynamics case. So we focus on the motivated by the recent Rydberg atom arrays experiments, we focus on the quench dynamics. And using the IPIP simulations, we obtained the equal time correlation functions. And from these results, we estimated the group and phase velocities given here. And by comparing our results with the recently updated Lieb-Robinson bound, we think that this Lieb-Robinson bound may be still not so tight, and maybe it seems that there seems to be a room to improve this Lieb-Robinson bound. Yeah, so this is my talk. Thanks for listening.
Okay. Thank you, Kaneko-san. So now time is open for discussion. So do you have any questions or comment? Okay. Okay, so I have a question. So in this slide, there are two propagation velocity for ferromagnetic Ising model and antiferromagnetic Ising model. So in the IPEP's result, there is a non-monotonic behavior appear, I think. So
you mean this kind of?
Yeah. They have a structure.
Yeah.
Why such a structure appears?
Yeah. To be honest, I don't know the origin of this kind of piece structure. Yeah. At the moment, we don't know.
But in the spin wave.
Yeah. I forgot to mention. Yeah, I forgot to mention. But I also did the spin wave approximations to estimate the Lieb-Robinson-like value. Well, this spin wave approximation was obtained first applying the Hochstein framework of transformation to the quantum Ising model. And after drawing a dispersion of the Ising model, we can estimate the propagation velocity from the largest value of the slope of the dispersion. The slope characterized the velocity, and so I think at the spin wave, for the spin wave calculation, the velocity shows a peak at the transition point. This corresponds to the transition point of the classical. I mean, yeah, the transition point of the Ising model. Yeah, so I'm not sure. Somehow it seems to show peak-like structure near the transition point of the quantum static model, quantum Ising model, but we are considering the dynamics of the quantum Ising model, so it doesn't have to be so, but somehow it shows this kind of peak-like structure.
Okay, thank you. So, Lee-san?
Yeah,
please.
Hello. Thanks for the nice talk. Just some question regarding this plot also. Like, so first I want to ask, so also for the second part of the talk, you guys are using simple update instead of before.
Yeah.
Okay. And I don't remember, I see the kind of the plot for the energy. Is the energy already off around this regime such that the result is...
So where is the energy? Just this is the energy conservation plot for the quantum Ising model. Oh, well, I just showed the ferromagnetic Ising model results, but for the antiferromagnetic case, it was similar. So I just showed the results for the ferromagnetic Ising model. And actually, for the short time up to around 4, the energy is well conserved. So, and the simulation was done for, where was the, I'm not here. I show the correlation functions for up to 3. So still the energy is conserved for this parameter region.
Okay, I see. It's actually quite surprising to me because comparing to the results using full updates, it seems that you guys match completely, like the results completely agree with each other.
Yeah, I agree with you. Yeah, it's even
do
the
you
simple
understand
update.
the reason why that's the case? Like, is it kind of for this parameter regime, it's the correlation dense is quite small, or?
I'm not sure. Maybe the state is not so entangled, even in the case of the quench dynamics to the transition point, but I'm not sure. But yeah, somehow even just using the simple update, we obtained somehow similar results.
Okay.
Yeah.
Okay.
Yeah.
My last question is actually a little bit deviated from tensor networks. That if I remember correctly, this plot that you taken from Marcus, there it's like the first version of their draft.
Yeah,
and the
exactly.
version of their draft,
they it's an archived version.
And they go up to time equals to 4. But the point is that in their results, they show that they can get longer time, at least that they claim that they get longer time convergence result comparing to the IPEPs using full updates. Do you have a comment on that?
Well, I didn't directly compare their results, so I cannot say anything. But concerning the applicability, we just use the simple update. So at least at the moment, their results may be much better. Concerning the simulation time, but concerning the finite size effect, finite size effect means this kind of size dependence. In principle, IPEP's algorithm would be much better because we basically consider infinite system, right? So, but there is some drawback. Shall we take the longer distance or shall we take the shorter? Well, for shorter time, or I mean,
Okay, I see. So there's still advantage of using IPEPs here.
Yeah, I think so. Yeah.
Okay, thanks.
Thank you. So do you have another questions or comment? Okay. Okuni-san, please.
Yes, thank you very much for nice talk. So I have a question about the first part. I think you calculated the correlation function, and usually the accuracy of IPEP's computation is well good around the central site on the infinite lattice. So my question is, do you look at the correlator just around the central site, or do you sum up contribution from all of the infinite lattice?
Sorry, I'm confused a little bit. What do you mean by center of site? I consider two site unit cells and calculated, for let's say sublattice A and sublattice B, and calculate the correlation from A and also calculate the correlation from the site B and average them. So
so this correlator means that correlation
so these are
within the unit cell.
Yes, within the unit cell. But we can take the longer distance, right?
I see.
Yeah.
Thanks.
Okay. Okay, so the time is up. Okay, so thank you, Kaneko-san.
Thank you very much.